My most recent fascination has been something called a Bloom filter. Some of you may know what that is, some of you may not. We're going to build one today in Zig. So I didn't know what a Bloom filter was until maybe about a month ago, and I've become more and more fascinated with them since. Not just because it has the word bloom in it, which some of my favorite things have the word bloom in it, like a bloom and onion from Outback Steakhouse, or In Bloom by Neck Deep, really great song, or Orlando Bloom. This, though, is about a data structure. So let's pull it up. So I've got the Wikipedia page up for the Bloom filter. There's a ton of information on here about Bloom filters. You can also find other sources. I was raised in a school that said Wikipedia is not a very good source of truth because anyone can edit it. However, I've found that generally Wikipedia is a fantastic source of truth because anyone can edit it. And I trust this pretty well. But there are other sources you could look at as well. So, in computing, a Bloom filter is a space-efficient probabilistic data structure conceived by Burton Howard Bloom that is used to test whether an element is a member of a set. False positives are possible, but false negatives are not. In other words, a query returns that it's either possibly in the set or it's definitely not in the set. Okay, so when would you use this? So one of the first things that comes to my mind is if you were to build an online game and you are setting up character names. So think about a game like World of Warcraft, where you can come up with whatever character name you want, and you can have multiple characters per account, but you got to make sure there's not duplicates, right? So if my character's name is Legolas, and I'm a Night Elf Hunter, because that seems to be a thing, I have to make sure that no other characters can be named Legolas, or else there's a naming collision. So if there are trillions of people playing the game, and each person has, I don't know, we'll say 10 characters, you can see that this becomes a problem if we need to query the database for all of these character names to figure out uniques. So an option here is a Bloom filter. So what you could do is you could essentially use this filter to hash the names and then flip the bits for your Bloom filter to indicate whether something exists. So that's a bit of a spoiler as to how this actually works. But the idea here is that Bloom filter is just an array of bits with a customizable size. So you can set it to, we'll call it M bits here, but you could do 128 bits. You could do something significantly larger. And the larger your Bloom filter, the more likely you are to delay false positives. Small Bloom filters will hit false positives quite quickly, and I'll show you an example of that today. But bigger Bloom filters will not, or should not. Once you have the array, you have k different hash functions. K is just another number that you can come up with. So the more hash functions you have, the better it is at preventing false positives as well. But you want to find a balance here, right? So hashing is generally not too expensive, especially if you're not doing cryptographically safe hashing. But it's still something that you want to balance. You don't want to spend your entire time hashing something over and over and over again. And you're flipping all of the bits that map to that hash index to true in this case, or to a 1. So the more hashes you have, the more quickly you will also run into false positives. So you gotta strike a balance, and that's one of the hard parts about a Bloom filter, in my opinion. It tells you here typically k is a small constant which depends on the desired false error rate, and m is proportional to k and the number of elements to be added. To add an element, you feed it to each of the k hash functions to get k array positions, and then you set all the bits to 1. That's it for adding things to the filter. It's really straightforward. So you can start to see that when we're working with bits and we're keeping our memory footprint really light, and we're keeping this all in memory, we're not having to query a database to check for naming conflicts for characters in a video game. There are actually quite a few other examples towards the bottom of this page that was really, really helpful for me because it showed even more cases where a Bloom filter is useful. And we'll get to those in a second as well. So to test whether an element's set, I'm sure you can imagine this, but you feed it to each of the hash functions to get those positions. If any of the bits at these positions is 0, the element is definitely not in the set. If it were, then all the bits would have been set to 1. So if all are 1, the element is either in the set or all the bits have by chance been set to 1 during the insertion of other elements, resulting in a false positive. In simple, for a Bloom filter, there's no way to distinguish between the two cases, but more advanced techniques can address this problem. We're not going to talk about those today, though. We're going to start with the basics. So there's some information about the space and time advantages. I kind of talked about these a little bit. When we're just working with a data structure of bits, the memory footprint is extremely light, especially when you think about the trade-offs of storing things in memory and having quick access to them versus reading from disk to try to find if something exists in a set. It can be quite a bit faster. There's some information on the probability of false positives and how to balance out this number. There's some formulas here. I won't get too far into these. We don't necessarily need to know them for our example, since our source code is going to be fully customizable, so you can plug these numbers in and adjust this simply by passing new values to the struct that we're going to work on. The thing I do want to get to is this example section before we get started. This one was really cool. I did not think about this. So the servers of Akamai Technologies, a CDN provider, use Bloom filters to prevent one-hit wonders from being stored in its disk caches. One-hit wonders are web objects requested by users just one time, something that Akamai found applied to nearly 3/4 of their caching infrastructure. Could you imagine if they were caching those one-hit wonders and the extra cost on disk, especially if you're caching them and then they're never accessed again? So what they do is they use a Bloom filter to detect when a second request for a web object has been created, and then they cache that object only on the second request. So the very first time you make a request to something backed by Akamai, it's not caching it. It's using a Bloom filter to keep track of what has been accessed, and then the next time it is hit, it will actually cache it. And again, there's no reason to cache something if it's never going to be hit again, so they are using the reality that something has been accessed multiple times before deciding whether they should cache it or not. Bigtable, HBase, Cassandra, Scala, Postgres, they all use Bloom filters to reduce disk lookups for non-existent rows and columns. Seems like a good use too. Chrome used a Bloom filter to identify previously malicious URLs. A URL was first checked against a local Bloom filter, and only if the Bloom filter returned a positive result was a full check of the URL performed. So again, using something smaller and in memory instead of going to a more expensive operation like a full check here. There's some more examples here. I think they're really neat. I could spend the entire video talking about those, and you wouldn't get to see any source code, and that's not fun for either of us. So let's get started. Okay, so I've got a new folder here called Bloom filter, and what we're going to do is run zig init, and I'm on zig 0.14.0 at this point. So with zig init, we get our build.zig, our build.zig.zon, and then we also get our main and our root. We're going to do everything in main, so we don't necessarily need the others. So let's go ahead and pull up source main.zig, and then I'm going to make this a little bit bigger for you all as well. Make this a little harder for me, but that's okay. Okay, so what do we want to do? We can grab all of this and delete it, and we'll start from a main method. So thinking about how we want to use this, we essentially want to initialize a Bloom filter, add some stuff to it, check to see if some stuff is found within the Bloom filter, and then kind of take things from there. So let's do exactly that. So we know that we're going to have like a Bloom filter, say Bloom filter.init. It's probably going to need an allocator, and then it's probably going to need a size. So we'll say we'll do 128 spaces in our Bloom filter for now, and we can toy with the size later. Since it's going to get an allocator, we know that we need to deinitialize it. So we'll plan to deinitialize it as well. And then we'll do something like bloom.add, and let's just work with strings. So we'll do something like Brad. Oops. And then we'll do something like standard debug print. Something like this. I actually don't know what the type is for a Boolean, so I'm just going to use any here, but I think that should be fine. So bloom check Brad. Okay. And then we can do something like standard. Let's just yank that and paste that. We'll do the same thing here, but this time we're going to do Jake. And what else? So we should see that Brad is true. Jake will be false. So let's go ahead and add Jake. And again, this all really depends on the hashing algorithm and the capacity of the, also yes, the capacity of the Bloom filter, but also how much of that capacity is in use. So we'll add Jake here, and then I will yank this again, paste this again, and then, yeah, we'll check for Jake again. I think that should cover it. Okay, so this is essentially what we're going to be doing in our main method. So we need to go ahead and create some things. So we have a Bloom filter that we need to create. We're going to make a struct for this. I'm going to call it Bloom filter. It's going to have items, and I'm going to use booleans. Keep things nice and simple. We're going to create an initializer. So we're going to take in an allocator. It's going to be a standard mem allocator. And it just occurred to me, whoops, that we probably need to import the standard library. Okay, sweet. So we have our allocator, and then we also have a size. So we're going to say that size is going to be a U size. And then it's going to return a Bloom filter or an error because we need to allocate space for this. So we can go ahead and return Bloom filter. Items is going to be equal to try allocator.alloc. The type is a bool, and the size is going to be size. My goodness. Okay, so far so good. We know that we have a dinit method, so let's go ahead and define that dinit method as well. So this is going to take an instance of our struct. So this will get a self Bloom filter, and it's going to get an allocator, and it's going to be standard mem allocator. The return type here is a void, and then we can do allocator.free self.items. We have essentially two methods that we need to build into our Bloom filter, which is add and check. So we're going to go ahead and start with add. And what I really want to do is use an iterator for this. So I think we're going to build a custom iterator. This needs to be a pointer. But we'll take this one thing at a time. So we're going to take in an item that's going to be a string. And the return type for add is going to be void. So let's just assume we're going to get an iterator here and make this kind of straightforward. So we're going to have hashes. I'm just going to call them H, I guess. So we'll have something like self.hashes, and then we'll take in an item. And then really what we can do, since we have an iterator here, is just do while hashes.next, get the hash value, and do something like self.items HV is equal to true. And that should set those bits for us, or set our booleans for us in this case. Check is actually going to be really similar, and the meat and potatoes of this is actually going to come down to that hash iterator. So that'll be fun to implement. But let's go ahead and implement check as well, because it should be fairly straightforward if we are using an iterator. So again, we get our Bloom filter, and then we get an item that we want to check. This is going to be a string or a slice of const u8. This one needs to return a boolean. So again, we can say self.hashes to get our hashes for an item. My goodness. Use another while loop here. So we can say while h.next, and we want to get hash value if not self.items hash value return false. Otherwise, we've finished our while loop, and then we can return true. I have a typo up here, so let's go fix that. I need to call next. Okay, I think that should take care of the interface. Let's go ahead and create that hashes function. And I actually think this is going to delegate to another struct. I feel like that would be cleaner, so I think we'll take that approach. So I have an item here. Again, this is going to be a const u8, and it's going to return, I'm going to call it a hash iter. And we have to create this, so we'll create it here in just a second. But a HashIter is essentially going to need like an item that we're working with and a maximum length to bound the hashes to. So, and essentially if we'll want a different hash every time, so we also need to keep track of the iteration. We could probably just do that. Well, all right, let's just add it here for now. So we can say iteration is equal to 0. So start on the 0th iteration. I don't know if we'd ever want to change that, but it's something we can configure here. The item is going to be item, and then the length is going to be self.items.length. And I'm missing a semicolon, so let's add that. Okay, cool. So it's yelling at us because we don't have a HashIter defined. Let's go ahead and define one all the way up here at the top. So this is going to be pretty similar. It's going to be a struct. So we have a HashIter. And really what an iterator is in Zig is something that defines a next method. So something you can continually call next on. So we'll do that. So we know that we want an iteration, which is a use size, and it's equal to 0 by default. We want an item. So this is going to be a const u8. And then we want a length, which is also going to be a use size. We just covered that, so that one should be fairly straightforward. We need a next function. So self. And one thing we can do here is, I probably need to start doing this more. I like this pattern a little bit better, using a pointer to @this instead of a pointer to the struct name. And the reason why is if I were to change the name of the struct, I don't have to update anything with the pointer to @this. But if I were to change the name of the struct, like Bloom filter, where down here I'm using, a pointer to Bloom filter, I have to change the name everywhere. So this @this is kind of nice at preventing that. Anyways, that's maybe a topic for another time. So we're going to return maybe a usize or a nullable usize. So what we're going to do is I just want to check. I'm going to set this equal to 3. We'll do 3 hash functions. And maybe one thing nice about this iterator and keeping track of the iteration is if you wanted to maybe use a different seed every time, which is what we're going to do, but you want to not hard code those seeds, maybe you want to programmatically generate them over time using maybe something like a Fibonacci sequence, for example. You could do that. In my case, for simplicity's sake, we're just going to hard code these for now, but I'll show you exactly how you could change this if you wanted to. So if our iteration is greater than or equal to 3, just return null. You can't. We're only supporting 3 hashes, so we don't need to do any more than that. I'm going to get a hash. I'm just going to call it H, and it's going to be a standard hash. Murmur32 seems like a great hash function to use. And we want to hash with a seed. And the seed is the key part because we need to make sure that we're consistently hashing against, well, the same seed for each step. So if we're passing Brad in once and then we're passing Brad in twice, but we're hashing with different seeds every time, we're going to get a different outcome. So we need to make sure that we're using a consistent seed. So in our case, we can use self.item for the value here. And then the seed is going to be something like seeds self.iteration. We'll have to define that in just a second. But once we end up hashing here, we can say self.iteration. We want to increment this by 1 just to keep track of what iteration we're on. And this will hopefully come together here in just a second when I put together an array for the hashes, or the seeds, I should say. And then we want to return the hash, and we want to modulus by the value that was passed in for length. So if we have 128 bytes, we want to constrain this down to 128 bytes. So 0 to 127 in our case for indices. Or I'm sorry, I said bytes. That is technically not correct, I guess. I meant the space of our Bloom filter, the length of our Bloom filter. So if our Bloom filter is 128 items, we want to make sure that we're operating on indices from 0 to 127. So this is just a way to constrain that to the length of the Bloom filter. Okay, this feels pretty good. Add a semicolon to make it feel even better. And then we need to define those seeds somewhere. So I'm just going to create an array up here, and I'll let it infer the length. And the seeds are U32s because we're using Murmur332. If you're using Murmur364, you need U64s instead. And And I'm just going to come up with some values. So we'll do like OXC70F6907. And then maybe like OXC15A9323. And then OXC04144444. Why not? That should be sufficient. And okay. I feel pretty good about this. I think the only thing we're missing is down here in the main method, we need to give this an allocator. So let's come up with an allocator. Okay, I think we're just going to use the debug allocator. So I believe that's standard heap debug allocator. Hey, sweet, I do remember where that one is located. We don't need to really configure it any particular way. And then we can make sure that we're deinitializing it here at the end. We need to get a handle on the actual allocator behind this debug allocator. So we will say debug allocator dot allocator to cast it to a generic allocator type. I think that's it. I'm not seeing any squiggles in my code, which makes me think that I don't have any errors. I'd be shocked if that's the case. I'm pretty good at typing up some Zig code, feeling confident, and then running it only to find that there is indeed an error. So let's give this a go. So if I zig build run and let this compile and see how this takes out. Okay, so no field or member function named add in this giant. Oh, I need to try. Let's go find that and fix it. So we have this Bloom filter in it. This can return an error, so we need to actually make sure that we're trying here. And if it does return an error, we can just fail out early because this is just me throwing together some Zig for you. You might want to handle your errors a little more closely if you're writing production code in Zig. Okay, so we have a Boolean output. This is great. So we have true, false, and true. This makes sense, right? So we have 128 spaces in our Bloom filter that we're working with. We put Brad in. So Brad is taking up 3 spaces. So for example, it might be space 1, 56, and 76. And then we're putting Jake in. Jake might hash into 4, 5, and 56. So in the case that we check Jake, we're checking 4, 5, and 56 the very first time here. And the only one being used is 56. So we see that 4 and 5 are not being used, which means that Jake is certainly not in the set. We add Jake, and then we execute it again, and we see that he is indeed in the set this time. So let's see if we can make this fail a little, not fail, but let's see if we can run into a collision a little earlier. So let's set our Bloom filter down to maybe a size of 3. Right quit, run this again, and we should see that every time it's true now. So if we were to look at this example again, we have 3 spaces, and for simplicity's sake, I'm just going to assume that it ends up being 1, 2, and 3. That's technically not the case. It could be 1, 1, and 1 in this example, or 1, 1, and 2, or 1, 3, and 3, or 2, 2, and 3. You get the picture. But for simplicity's sake, since we did run into a collision, let's just assume that they're the same, and we can assume that they're 1, 2, and 3. If we really wanted to know, we could add some code to print out the internal structure of our Bloom filter as well, which might be fun too. So if we have this example, we check and see, we add Brad, and we check and see if Brad's in there. He obviously is, because we just added him. But he's also taking up all the available indices in this example. So if we check to see if Jake is in there, we get a false positive, because there's no free indices, which means the values that we're hashing Jake to are the same values that we're hashing Brad to. So we have a false positive in this case. We can still add Jake because our code does not prevent us from adding something that already exists. It also doesn't necessarily need to. If the values are already true, setting them again to true is not really doing anything except maybe wasting a little bit of CPU cycles. So you could optimize that there too if you really wanted to. But again, we add Jake and then we check, and yeah, he's certainly in there again. So let's crank up this Bloom filter one more time to something like 512. We run it again, and we should see yet again that it's true, false, true. And there is a chance, a tiny chance, depending on that hash function and those seeds, that even with something like 512, it ends up hashing to the exact same indices for the exact same, hashing to the exact same indices, even though the inputs are not the same. So there's always a chance that if I tinker with some of these values and run it again, you might see true, 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 even if we're working with a giant Bloom filter. Anyways, this is it. This is a Bloom filter. So I just wanted to take some time to show you something that I've been fascinated with and build a little implementation of a Bloom filter for you and also for myself. Gives me an excuse to write some Zig, which is great. I've been doing a lot of Go lately, and I still enjoy Go a lot. But yeah, I've been missing Zig, so it's nice to get back to it. Anyways, I hope you found this video helpful. I would love to know what other data structures you are interested in. I have, maybe it's not a secret, but I've also been exploring B+ trees, and I find those absolutely fascinating. I still am struggling to understand exactly how B+ trees are used by databases. I understand that they're pointers, and they're keeping pointers to pages on the file system, essentially, but have a bit of a hard time wrapping my head around exactly how that works. So that's currently what I'm looking into learning more about. If you're learning anything interesting or have found some really cool data structures and want to share those, I would love to learn more about them in the comments below. Thank you and have a great day.